Hi everyone and welcome to our talk on database and cache internals. Today we are going to see the numbers we've got when we compared ScyllaDB and Memcached and as well as discuss how the results actually drill down to which solutions design decisions. So a quick intro about ourselves. I am Felipe Mendes, ScyllaDB committer and also a co-author of Database Performance at Scale. This is my puppy here out of the picture and despite his mean look, I assure you that he's adorable. So, as you guys can imagine, I know lots of things about ScyllaDB, but not so much about caches, which is why, Alan, thank you for joining us today. A few words about yourself.
Hi, I'm Alan. I also go by Dormando on the GitHub and the mailing lists and various committers everywhere. I've been maintaining Memcached since 2008, roughly, and I've also worked on MobileFS and Perlbell and Gearman and a bunch of other different infrastructure projects and Perl things. I worked for Fastly for quite a while as a director of engineering on their cache service, and so I'm very familiar with cache systems and also familiar with databases as it has to be.
So, the context of today's talk was basically originally inspired by the talk that Danny Cooping from Grafana Labs presented last year. If you didn't have a chance to watch it, I highly encourage you to take a look at it when you have a chance. And Danny shared how Memcached, they basically scaled up dramatically while using Memcached while still reducing costs. So after Danny's talk, we basically came up with this brilliant idea of, okay, so let's compare ScyllaDB and Memcached. In one sense, because Danny's talk basically made the case of using XStore in order to extend Memcached memory and also to disk. And ScyllaDB and other databases have basically been using disks for quite a long time, right? But how we actually could run these tests. And you guys probably know that the benchmark industry probably has some problems, right? And we didn't really want to just come up with work just by ourselves here on the ScyllaDB side, which is why basically we reached out to Alan Dormando on Slack, and we decided to carry out together. So yeah, and that's basically the context of how we actually got to this talk today. So jumping into the actual numbers we've got, so starting from the basics, which data store has a more efficient memory utilization? We started by basically testing a simple key value workload, and these are the results which we have got. So basically, in a nutshell, as we can see, Memcached had cached 101 million items before evictions actually started to happen. But ScyllaDB on the right-hand side cached only 61 million items. And there are several reasons for that. So for example, while ScyllaDB has its own LRU cache, just like Memcached, ScyllaDB as a database also needs to support a wide column data representation, meaning that a single key may contain many rows. And because of that, and also other protocol overheads, this in turn actually causes Scylla, a single item on Scylla, to end up consuming more space than a single item on Memcached. If we drill down on the differences, here you can see that Memcached basically we have very little overhead per item that you store. So in this example here, this output that you see on the screen, it's basically 48 or 56 bytes, depending whether you have CAS enabled or disabled. But on the right-hand side, we can see that ScyllaDB basically has lots of things it needs to manage. So it has to allocate space for its main tables, Bloom filters, SS table summaries, so that in case a cache miss happen, ScyllaDB knows how to efficiently retrieve the data on disk, since it's not available in the cache. And in addition to that, we also support a richer data model, which is basically range continuity, so we can support range queries, timestamp information, liveness information, TTL, complex types, user-defined types, and so forth. All right. So after we basically measured the cache effectiveness, we then moved on to actually compare the performance of both data stores in an in-memory read-only workload. And Alan, I know that you have some reservations about how the test was carried out here. And I would like to get your opinion and your feedback over the numbers presented here.
Yeah, so this was probably the biggest point of contention throughout the entire discussion on your blog work there. I will start by saying so we're using very different tools. You have Cassandra Stress, we have Shredder, which is a tool that I wrote for emulating different workloads to help me more stringently test memory backed storage, flash storage, or our new proxy product. And so Mendes may not be measuring things quite the same way to begin with. And we also usually approach things differently by rerunning the same test at different request levels, request rates, and seeing like, oh, how does the P99 change as we do this or that. But mainly, you are fetching these clustered keys, right? So you have one key that is actually fetching 16 different keys at once. And on the Memcached side, we're actually fetching 16 piped requests from 16 completely different areas in memory. And so this may or may not make sense based on how your actual application works. Like you may not have the opportunity to split or coalesce your cache data close enough for that kind of a test to make sense. On the other hand, if all these keys are really very closely related and are never fetched outside of each other, for a Memcached use case, it might be better just put all that data in one key on our side, in which case our memory overhead gets even less. So, but as for purposes of this test, we went back and forth on it quite a lot, and it looks like this is actually the closest we could get to fair.
Yeah, no, exactly. I do feel like I do have to provide you and also whoever ever sees this work an explanation, right, of why we did that. So first, of course, when we tried to run this test, we tried, hey, let's do it key value on Scylla and also key value on Memcached, which is how it was carried out on Memcached. But on Scylla, I quickly realized that it wouldn't get to actually saturating the NIC. And after I dig through what was going on, I eventually realized that, hey, basically the Memcached test is benefiting from the Memcached, basically Memcached pipeline feature, right, where you can basically pack several requests under, several GET requests under a single TCP packet. And CQL, which is the protocol we use it here, basically does not introduce this concept of pipelining. Although the CQL protocol does support multiplexing many parallel requests over a single connection, but it's not quite the same because doing it so would easily overwhelm the NICs packets per second, right? On top of that, ScyllaDB follows this shared notching and shared per core architecture, which basically, upfront from the comparison, it's like we are comparing a sharded system versus a shared everything one. And it's funny because we basically compared single node Memcached versus single node Scylla. But even then, because ScyllaDB decided to take this architectural approach, this also makes it even harder to support things like pipelining. So we did have some alternatives, such as, for example, I could increase the payload size from 1 kilobyte to something that larger, but that would simply masquerade the problem, and I think that wouldn't be actually ideal, right? And another option would be to actually scale the tests to more instances and shard it. That would be more expensive, but could be somehow in line to how people are actually using Memcached at scale. But in a way, I was reading from the Memcached wiki that if you guys are basically doing consistent hashing on Memcached using, I don't know, Memcached proxy or something like that, then you may end up on the very same situation, right? Because if you are doing a multi-get, you may actually hit several replicas. So you could have some bad latency in there. Is that a correct understanding, Alan?
I think we can get into that in the next slide, actually, if you want to jump ahead.
Yeah, no, that's true. Given those differences, right, I think one particularly and interesting aspect is that, well, Memcached and ScyllaDB actually recommend exactly the opposite thing, right? So while pipelining is the best of the words in Memcached, that's how I assume it. In ScyllaDB, we actually recommend parallelizing requests with very high concurrency. So I took this example from the Memcached wiki itself. But I mean, if I move over to the next slide, then we get to actually to shard or not. And I guess that's when you may want to chime in, Alan, because as I said, ScyllaDB has the shard per core architecture. So even a single node, you already have sharding. How does it work for Memcached?
So for Memcached, we went past that previous one a little quick there, but if you queue up all of your keys at once and you tell your client, say, let's fetch 50 keys, and you have 10 Memcached servers in your Memcached pool, the client will actually parallelize 10 requests per server. It will make 10 pipeline requests per server and do some things in parallel and some things pipelined. And that's just how that works for certain operations. But we typically don't shard. Our sharding is just a consistent hash, and you go directly to a list of servers, and you fetch your keys very directly. There's no chatter, there's no overhead associated with managing your clusters. But in the last 10 or so years, or maybe longer at this point, a lot of companies are multi-regional, they're multi-availability zone, and you might have disasters where some zones go up and down, or you have users who are in different zones, and you kind of want to keep your cache at least consistent and replicate, like, say, deletes across different zones or sets and keep your cache fresh, or fall over if there's a local disaster and you come up with no cache. And so we have this proxy that is now built into Memcached, which is very simple to deploy and can, in some cases, take over from a more complicated client, and you no longer have to do like your own kind of sort of basic level replication for sending requests kind of near or far. Or in the case of Xstore, you might have a lot of small memory that that you're going to be fetching all the time, but you want to have some large, like these 1.5 megabyte keys that Danny was working on, and maybe those don't belong in the same clusters. And you can use this proxy to route certain requests from pool A to pool B, and pool A is memory only, and pool B is Xstore.
Yeah, that's great. So right after we were done with our in-memory tests, that's when we actually decided to introduce Memcached Xstore in the picture. And at the same time, we also shifted the workload on ScyllaDB to also read mostly from disks. It's worth to mention here that from this point forward, we actually reverted back the ScyllaDB testing to single key value gets. So the previous clustering approach, which we've took, wasn't done for the particular individual for this particular set of tests. And we started with a really small 1 kilobyte payload. And I read in the Memcached documentation that this is somehow it's Achilles heel, which is, for a better term of it, maybe not a good fit for XStore. But even then, even with a small payload of 1 kilobyte, I saw a good improvement of 11x if we compare how much data we actually cached in Memcached, as opposed to if we were not using XStore. And with regards to the tests itself, I mean, I think that's exactly where pipelining somehow introduced some level of contention. We can see here that the latency on Memcached side was a bit higher with pipeline requests. I assume because we either introduced contention on the disk level or in the XStore IO threads. But when we were not using pipelining, I mean, the performance was just great. So, Alan, do you have any observations or with regards to this?
Some users have payloads all the way down to a couple hundred bytes, and they still use XStore because, if you can cut your RAM in half, that cuts your costs quite a lot still. So even if you're not filling your whole disk, you can still get quite a lot out of it. And as far as these pipeline latency, so if you're doing like 32 pipeline requests against XStore, it actually has to go and fetch all of those things from disk before it can start to respond. So you're actually seeing the tail latency instead of the head latency there. It's something we might fix in the future, but it's not something that comes up all that often.
All right. So let's now talk about I/O access methods, because ScyllaDB uses asynchronous direct I/O, which previously we blogged about in the past. Here's the link from an article from our from Avi. But in a nutshell, I mean, the thing about using asynchronous direct I/O is that ScyllaDB at the end of the day is a persistent database, right? And we do need to persist your data. Otherwise, I assume it would be really bad reputation for a database if we actually lost data. And this includes optimizing for disk things like optimizing compactions, write-ahead log, efficiently retrieving data from disk, etc., and so forth. So those have been the original motivations for us to use asynchronous direct I/O. And then in the middle, we have this user space I/O scheduler, which basically arbitrates which and how much I/O capacity is given to a given internal or external user-facing competing workload. How does Memcached XStore actually issues I/O, Alan?
We try it very simply. So we do almost nothing, and we need to do I/O actually very infrequently. So you can delete and overwrite and update the TTL and keys and things without ever touching the disk. So because we don't need to do that, we can go with a very simple scheduler. And you might have to tune the number of XStore threads, the I/O threads that we have in order to maximize your disk. So if you roll it out and you say like, okay, my disk doesn't look fully utilized, and we still have a lot of CPU free, you can just up that thread number and then try again. And at some point, I think we'll get that to be more dynamic and let it self-tune.
Perfect. And I think this slide basically explains how simple it is, right? I think you added this slide for some context.
So XStore is additional. It's like kind of bolted onto the existing RAM cache. And so we still have this RAM cache available, and we make use of that to reduce the amount of disk I/O that we have to do. So if you have, say, 5 gigs of RAM, and you have 1 gig of that is dedicated to these small pointers that you can see in here, that point from memory into disk, and you still have a couple extra gigs left over for RAM cache. If you have a user who's clicking around a website and changing the cache around, they might never actually go to disk. You might only go to disk when they leave for the day and then come back later. And the next day, it'll pull their cache entries from disk and start again. So we can be very efficient this way.
All right. So our last results for today actually show XStore and ScyllaDB side by side with a larger 8 kilobyte payload in size, not as large as Dennis, which was doing megabytes. But even then, I mean, Memcached achieved 25x savings, which is super impressive, and really low latencies when pipelining wasn't involved. And again, I assume that with pipelining, that was due to disk or XStore IO thread contention. I didn't dig into that. Whereas ScyllaDB again maximized IO and a P99 latency of roughly 2 milliseconds per request. All right. So who won or who lost? That's typically the conclusion of most performance comparisons out there. But I mean, the overall idea of this work is that we believe it makes very little sense to actually call out our winner. And for a variety of reasons, right? We do recommend you to watch our full report, as it contains much more details about internals and the trade-offs involved in each solution's decision. And with that, a few takeaways before we wrap up. So we hope this work somehow inspires industries to adopt a different approach on performance testing. In our case, as we've seen, database and caches are very different animals. At the end of the day, inevitably, just comparing performance is often not enough. It's hard to express your reality just from simple performance comparison tests. And every optimization has some degree of sacrifice. For example, pipelining is great, but on Nextstore, as we've seen in the numbers, it easily introduced some I/O contention. ScyllaDB shared per core and complex data models are also great, but it does sacrifice things like pipelining and add some level of memory overhead. However, an interesting fact that I realized after when I was doing these slides is that the numbers, the performance we've seen here from Memcached and Scylla were actually much lower than the numbers that Danny shared. And again, their use case is different. Alan mentioned about their very big payloads. So probably that's something that is in their own reality, right? So all those comparisons and those numbers that we are discussing here can get very subjective as times go by. So with that, thank you for watching. That's what I had to present. And Alan, any final words for our audience?
Thanks. It was fun being here. If your company has any questions or needs any support, Memcached is supported by me full time. You can head over to cacheforge.com and reach out.